explanation in this class. All right, so we did, this is the most important one, exploiting vulnerable server on Windows. And so let me just talk about the others. Here, you can defeat data execution prevention with return-oriented programming, but the technique used here only seems to work on old systems like Windows 2008, not Windows 2016. So it's not all that important. If somebody knows how to modernize this, I'd like to know how. This was the real joy of Mona. Mona had this ability to create ROP chains. But as far as I can tell, they don't work on modern versions of Windows. So here, you turn on data execution prevention again. You inject NOPS and CC just like we did. And when you jump to it, it won't run. But you get to the int3. This is what happened when we did it today. It went to the int3, which ran. But if you turn on data execution prevention in advanced system settings and run it again, it will stop right at the NOP. It will not execute the NOPS and get to the int3. It will stop there and say access violation, which means you are trying to execute code in a non-executable memory segment. So it's a permission violation. So the cure for that is to make a ROP chain which turns off the Windows defenses. And they use these functions, virtual alloc, virtual protect, write protect memory. These are Windows API calls that change the permissions of a memory section. So in principle, you can paste together little pieces of code to create a function call that will turn off the defenses. And it sounds good, and Mona has the ability to find these ROP chains. It will take a few minutes to run, and it will find these ROP chains for you. So you have a series of addresses, and each of these addresses will have just a couple of assembly language instructions, and all this junk put together adds up to something. So here I found the virtual alloc worked. I think it was the virtual protect was the one that worked on Windows 2008. It gives you a series of them. So this is the register setup that will do it. And there's the ROP chain. It's just a series of addresses. So instead of, we did a trampoline where you jump to one command that's jump ESP. And this is just a longer version of the same thing where you have 20 or 30 of these things, which add up to a system call that turns off the defense. It sounds great, and it works in 2008, but I can't make it work in later versions of Windows. So that's less important than it used to be. Then you can learn about stack protections. You can compile code in the Visual Studio. Gives you a command line compiler, just like GCC, which is bloody awesome. If you want to understand things, you can make the same programs we used in Linux, very similarly, right in Windows, compiling them with the CL command line tool. And you can make simple buffer overflows here and other defenses. You can use IDA Pro to look at it. So the first thing I did was compile it by default and then compile it with the linker, PWDN, with GS-. That turns off stack cookies. Stack cookies are one of the defenses to prevent buffer overflows. So if you look at Windows code that's compiled with the default stack cookies, then here's what a subroutine looks like. This subroutine is going to ask you to enter a password and then try to decide if it's right. And every subroutine that has a string that looks like it might be vulnerable, the Windows compiler will automatically add a security cookie to it. So when you first enter the subroutine, it will fetch a random security cookie value, store it somewhere else to remember it, and put it on the stack at the end of the stack before the saved return pointer. And then at the end, when you return, it will check to make sure that cookie has not changed before it returns. So this way, the buffer overflows we've done that run through the whole frame and change the return pointer will not work anymore. So you can see that this is with the security cookie. And if you turn it off with the GS- switch, you get this simpler routine that doesn't have that cookie in it. So you can choose to compile, all right, you changed the 0 to a 0.1 and it still worked. Well, that's very strange. All right, anyway, I don't know what's happening there. Anyway, so then you can do ASLR and you can scan the limitations of ASLR. These are a few more fun things to try. Here I wanted to see, let's see, 302 first. You can observe address space layout randomization. by making a program that prints out the stack pointer. And you can do it by just including assembly code inline in your C code. So this will copy the stack pointer into a data variable that's defined as an integer, and then you can refer to that data variable here. So that's a way to print out the contents of a register, and you can see that ESP keeps moving. So by default, when you compile a program on Windows, it has address space layout randomization, but if you choose to compile it without address space layout randomization, you compile it with different switches and you link it with dynamic base equal no, and now it will not be randomized. So that's kind of good, clean fun. And you can, in fact, make a buffer overflow exploit the same way we've done and see it happen there. And you can test the quality of Microsoft's randomization. Microsoft's address space layout randomization in early versions was pretty lame. It only had 256 possible locations. So you had a pretty high chance of just getting lucky if you could run your exploit a few hundred times. But you can see how good it is now, and it turns out to be pretty good. You can compile it with randomization and then use Python to run it 10,000 times and see how many of them are near the expected location, and it turns out to be quite good. Anyway, so you can test the quality of Microsoft's defenses that way. And here, the last one I think I'll mention today is the SSH Base exploit. This is actually another interesting Windows vulnerability. And in fact, I think I can show you a little bit of this. So we still have a Windows machine here, and it's still running vuln servers. So I'm just going to go debug, restart, and run and run. And I think I can show you some of this one. So we're going to just attack a different function. Last time we did trun, and trun had a classic stack buffer overflow. Gmon is the one we're going to attack now, and that's SEH1. So let me see if I've got it in my list of things all ready to go here. LS, I say. I don't have it, but I'm going to put it there. Let me just copy a VS shell to SEH1. I want to get the address right. All right. And so now I've got this junk right that does the server S port. All right. And then let's get rid of all this. Then it's going to do the connect and all that stuff. I think I can just put all of this here. That should do it. All right. There, that should do it. I don't really need to worry about after I send it, closing it or anything, because I'm planning to make it crash. So let's see what that does. All right, and sudo, I don't need to, I can just do /SEH1. All right, let's see if that works. So my Windows is here, and my attack is here. And if I run this attack, good. It gives me an access violation. And what's going on is it has made an illegal instruction. Now I can view the SEH chain. And what this is the structured exception handler. So let me restart it to get a clean one so I can explain what's going on here. Max my CPU and debug, restart, and run, and then view SEH chain. Now, what happens in Windows is when you have an error of some kind, like a divide by zero, or the kind of errors we've made here, attempt to access invalid memory address, or so on, that creates what's called an exception. The exception is passed to your program first. Your program can define exception handlers. So if an error happens, your program will handle it internally. And that is done in the form of a chain of addresses. So it tries this address and that handler, then it goes to the next handler, and if it fails, then it goes to the operating system, which will then print up some Windows-based error message. So you have the exception handler, and the exception handler is stored in memory. And you can sometimes have overflows that hit the exception handler, and that's what happened here. So here's the valid exception handler going to code and region of 72C. But if I send in this attack, it crashes the exception handler. So right now, the right answer is 72cc, and my code is running. But if I send this in, it crashes, and it tried to go to this invalid place. And if I go to the SSH window, you can see now some of the data I put in was B, C, D, E. So I'm able to inject data into the exception handler, and something about my code caused a crash, which raised an exception. So it's another way to get control of the instruction pointer. And it was especially important in earlier versions of Windows because even when a lot of things were randomized, the exception handler was always placed in the same location. So it was something you could find. So exception handler exploits were particularly useful. Anyway, so you can inject Metasploit payload there and take over machines the same way. And you can use .NET if you like, which is a higher level language. And you can do ARM shellcode, which is kind of mind-bending and good for us to get used to. ARM is more and more important. And the Raspberry Pi is nice for 32-bit ARM, the older Pi I had, and I'm using an iPhone for 64-bit ARM, and you can do buffer overflows in both of those if you have access to the hardware. So that's all I wanted to show you. I'm going to stop the recording.